These are the notes for AP Calculus on the topic of the summary of all the convergence tests for infinite series. So let's take a look at all of them and just review each one of them real quick. So the divergence test, which is also sometimes known as the Nth Term Test, this is kind of the most basic of the convergence tests. It basically says if you take the formula there inside your infinite series for finding each of the terms a sub n, and if the limit as n approaches infinity of that formula does not equal 0, then that guarantees the series is going to diverge. Because if the terms are not getting smaller and smaller approaching 0, that means either they're staying the same or they're increasing. And so if that's the case, there's no way it can converge. It would have to diverge. However, notice, just because it is equal to 0 doesn't guarantee it converges. It just means it might converge. And we'd have to use one of the other tests to determine if it in fact converges or not. The next test is the integral test. So if the function is positive, continuous, and monotonically decreasing, so it's decreasing the whole way, and a sub n equals f of n. So here, this series here is f of n. Basically, this is saying, it's called the integral test. If you integrate from the same limits, in this case from 1 to infinity, if you find that this definite integral converges, you know the series would also converge. Or if the definite integral diverges, the series would also diverge. So if you can integrate easily the expression that's inside that gives you the formula for each term here, a sub n, then either series both converge, the series and the definite integral both converge, or they both diverge. So this is if it's easy to integrate what's in there. Next is the p-series test, one of the simpler ones. If you have a series in the form 1 over n to the p is the power there. If that power on the denominator there of n is greater than 1, the series will converge. However, if it's less than or equal to 1, the series will diverge. Then we've got a geometric series test. Well, geometric series are when the terms, keep getting multiplied by the same thing. So, for instance, 3, 1, 1/3, 1/9, 1 over 27. That would be an example of a geometric series. Where the common ratio, you can see each time it's being multiplied by 1/3. So the common ratio with r is 1/3. So if you have an infinite geometric series, it goes on forever. This is saying, once you find that common ratio, which is whatever's being raised to the n or n minus 1 power, the series converges if that ratio is between -1 and 1. Okay. If it's not between -1 and 1, then it will diverge. That's because if the common ratio between -1 and 1, as we can see right here, the terms are going to continue getting smaller. But if it's equal to 1, -1, or greater than 1, or less than -1, the terms in size will be getting larger. And if that's the case, then this is the one where you can actually find the sum. It's a sub 1, which is the first term, divided by 1 minus the common ratio. Next, we have the alternating series test, like the name suggests. Alternating because the terms alternate between positive and negative. And the first term could either be positive or negative, but they alternate. And what's causing it to alternate is when you have -1 to the n, or sometimes the n plus 1, or power. That's what's causing it to alternate. Because if n is 1, you'll have -1 to an odd power. If n is 2, -1 to an even power. 3, -1 to an odd power, and so on. That's what causes the series to alternate. So we're defining here a sub n to be the rest of the formula. That doesn't include that part that makes it alternate. And the alternating series test, there's two conditions that have to be true in order for it to converge. First, if you find the limit of this formula right here, and that equals 0, that's one of the conditions to be true. And what this is saying is a sub n is greater than a sub n plus 1 for all n. In other words, a sub 4 would be greater than a sub 3. A sub 3 would be greater than a sub 2. So each term is greater, sorry, I got that backwards. A sub 3 would be greater than a sub 4. So each term is greater than the term after it. In other words, the terms in size keep getting smaller, regardless of the positive or negative. So usually if you find the first three terms, you can make that determination. So if both of these conditions are true, the limit as n approaches infinity of a sub n equals 0, and the terms keep getting smaller, then that guarantees that the alternating series converges. However, if either one of these two conditions above is not true, then the series diverges. Next, we've got our ratio test. So here, you just substitute in n plus 1 into wherever there's n in your formula, and then divide it by the original formula, a sub n right here, and take the limit as n approaches infinity, the absolute value of that. Well, you'll get some limit. And if you get some limit that's positive there, or equal to 0, so it's not negative, and you will because of the absolute value signs. Then, if that limit is less than 1, the series converges. If the limit is greater than 1, the series diverges. However, if it equals 1, the results are inconclusive, and then you'd have to use another test. The root test is very similar, except here we take the nth root of the formula and find the limit as n approaches infinity. Again, you get some positive limit out of that, L. If that limit, just like the ratio test, if that limit's less than 1, the series converges. If the limit's greater than 1, the series diverges. And if L equals 1, the results are inconclusive, and using the root test, then you'd have to use a different test. And our last two tests are both comparison tests. So these are always used together with another test, in conjunction with another test. So direct comparison is when you know for sure that what you're comparing it to is either less than or equal to or greater than or equal to the one you're comparing to for all n. So here you can see a sub n here represents this one that's smaller, b sub n represents the larger, the one that has larger terms. So what this is saying, if the series with the larger terms, which is right here, converges, then the series with the smaller terms right here would also have to converge. Okay, and it works the other way around. If the series with the smaller terms diverges, then you know that series with the larger terms also diverges. And the final one, the limit comparison test, this one's better when you can't tell for sure that one's always going to be greater than the other, or you can't tell at all which one's going to be greater than the other, unlike the direct comparison test. So a sub n and b sub n. A sub n is the original one, and b sub n is what you're comparing it to. It could actually be either way around. And when you find the limit as n approaches infinity of their ratio and you get some limit, if that limit is positive and not infinity, okay, another way to write that would be it's between 0 and infinity, then both series converge or both diverge. So you want to compare it on both this comparison test and the direct comparison test to a series that's simpler, and it's easier to tell using one of the other tests whether it converges or diverges. Okay, let's look at some examples and see how this works now. So these say determine whether the series converges or diverges, and then state the conditions of the test used for determining convergence or divergence. So we're going to go in a little more depth, like a free response type of question, where you actually have to explain how that test guarantees it converges or diverges, not just which test it is. All right, so let's take a look at this first one here. We've got the series from n to infinity. And if you take a look at this right now, it doesn't apparently fit doesn't fit p series exactly, or geometric series. It's not alternating. So it doesn't seem to fit any of them right off the bat. This is not one you could easily integrate. So when that's the case, when it doesn't seem to fit any of the ones there, usually that means it's going to be one of the comparison tests. So let's see, think as n goes off to infinity of this series, what terms are going to matter? So from n equals 6 to infinity, well, the 5 on the numerator is obviously going to matter. That's the only thing that's on the numerator. And when you head up to infinity, the term with the highest exponent is going to matter more than the other. So it'll be 5 over 3n squared. The other terms will end up being negligible. So let's compare to that, which is a little simpler. And remember, just like with the integrals, constants multiplied, in this case 5/3, those can be pulled outside of the series as well. Because that 5/3 will not affect whether the series converges or diverges. All it's going to do is multiply every term by 5/3. So this is essentially the same as we pull the 5/3 on the outside, and then we have the sum from n equals 6 to infinity of 1 over n squared. And now you can see this fits a p-series test, 1 over n squared, where p equals 2. And since that's greater than 1 by the p-series, that means this converges. So what we use here so far now is we're comparing it to this one, but we haven't decided whether to use the direct comparison test or limit comparison test. So can we easily tell whether this one's always larger or smaller than this one? Not really, because we've got a minus 4n and then a plus 2. So depending on what n is, that could determine which one's bigger or smaller. So when that's the case, that's where you want to use the limit comparison test. So we're just going to compare it to this. And with a limit comparison test, remember what you have to do is find the limit as n approaches infinity of our original one, 5 over 3n squared minus 4n plus 2, the ratio of that divided by the one we're comparing it to, 5 over 3n squared. But that's the same as the limit as n approaches infinity, 5 over 3n squared minus 4n plus 2 times the reciprocal, 3n squared over 5. All right, then let's see what simplifies there. You can see the 5's reduce out. And then when you substitute infinity, the terms that are going to matter most on the numerator, it's going to be 3 infinity squared. That's the only term up there. And the denominator, the negative 4n and 2 are going to be much smaller than 3n squared, so it'd be 3 infinity squared. And then you can see everything reduces out, and you just get 1. And that is greater than 0, and it's not infinity. So you can use the limit comparison test here, which says both series converge or they both diverge. Since we know this series converges by the p-series test, our series would also have to do the same thing and converge. So let's state this and then state the conditions. So we could say the series converges by the limit comparison test since, let's explain the conditions of the limit comparison test first, and that was since our limit right here, the limit as n approaches infinity of 5 over 3n squared minus 4n plus 2 divided by 5 over 3n squared. Since that limit was between 0 and infinity, so that's, we could say it's 0 is less than that, which is less than infinity. In other words, it's between 0 and infinity. In this case, we got 1. Okay, and we also use the p-series test. And the reason for that converging was since our p-value, which was equal to 2, was greater than 1. Okay, let's take a look at another example. On the next one, it says determine whether the series converges or diverges, same thing, and state the conditions of the test used for determining convergence or divergence. So this one, right off the bat, because of this negative 1 to the n plus 1, that's what tells you this is an alternating series. You can see if you substitute n equals 1, you'll get 2, n equals 2, you get 3, n equals 3, you'll get 4. So we're going to switch back and forth between even and odd exponents, which is going to cause each term to alternate between positive and negative. So in this case, what's left is just this 1 over n, and that's our a sub n right there. We're going to use. So remember the alternating series test, there's two things we have to do. We first find the limit as n approaches infinity of everything but the thing that's causing it to be alternating, so just 1 over n. And on that one, you can see, if you substitute in infinity, we do get 0. Okay? So that means it might converge, okay? Since that limit does equal 0. But then we also have to see if the terms continue getting smaller. So if we find the first three terms, a sub 1, a sub 2, a sub 3, if you substitute in 1, we get 1 over 1. If you substitute in 2, 1 over 2, 3, 1 over 3. So the terms do keep getting smaller. So you could say this series converges by the alternating series test since our limit as n approaches infinity of 1 over n does in fact equal 0, and we can write it in general terms here, a sub n is always greater than a sub n plus 1 for all n. We should probably establish that a sub n, just to be clear on this, is 1 over n. All right, let's take a look at the next one here. We've got 1 over the cube root of n. Well, notice that's the same as 1 over n to the 1/3. So you can see this fits our p-series test with p equaling 1/3. And since that's less than or equal to 1, we know by the p-series test this diverges. So we can say this series diverges by the p-series test. And then let's state the conditions of the test since, we kind of wrote it already, but since our p-value equals 1/3, and that's less than or equal to 1. All right, let's take a look at the next one here. Next one, we've got e to the n plus 1 over e to the n. So right now this doesn't seem to fit any of them exactly. It's not p-series, not geometric. Doesn't look like one we could integrate that easily. Although this one's not, actually you could integrate this one if you were to, I just realized if you were to split up the fraction, divide them both by e to the n, you could split into two integrals and use the integral test. So sometimes there are more than one way to go about these, more than one test that would work, but I think easier than an integral test on this one, I think will be a little simpler if we use one of the comparison tests. Because if we just take off this plus 1, which as we head off to infinity is negligible, look at what's going to happen. If we compare it to n equals 1 to infinity, I'm just taking off the plus 1, we have e to the n over e to the n. But that simplifies to just be 1, right? Well, if we have 1 there, well, how can we tell if that converges or diverges? Well, we can use the most basic test, find the limit as n approaches infinity, our divergence test, or nth term test. And if you find the limit that approach infinity of 1, well, there's nothing to plug in infinity into, substitute into. So this is just going to be 1. Because here, all the terms are going to be 1. It's going to be 1 plus 1 plus 1 plus 1, which you can see would just go to infinity. It would diverge. So this diverges by the divergence test, or nth term test. And let's take a look at this one. If we add 1 to the numerator, that's going to cause this one to always be larger than this one. So that means since the smaller one diverges, the larger one would have to also diverge. So by the direct comparison test. So we could say the series diverges by the direct comparison test. Since, all right, in this case, what we found is 0 is less than the smaller one was 1, which is less than e to the n plus 1 over, less than or equal to, I should say, over e to the n for all n. This is just saying the one we're comparing it to is always smaller than our original one, or our original one is always larger than what we're comparing it to. And the divergence, or I could also call it the nth term test, since the limit as n approaches infinity of 1, the key was in order to possibly converge, this had to equal 0, and it did not equal 0. That's how we knew it diverged. All right, let's take a look at the next one. On the next one, we've got pi over sine of 2 to the nth power. So on this one, we can see, well, pi over sine 2. Well, both of those are constants, aren't they? So let's find the first 3 terms and see what's happening. So if you plug in 0, that's going to just give you 1. If you substitute in 1, that'll be pi over sine of 2. If you substitute in 2, be pi over sine of 2 squared. So notice what the pattern is. You're multiplying by pi over sine 2 each time, right, to get to each term. And since you're multiplying by the same thing each time, this is geometric. And our common ratio is pi over sine 2. Well, let's approximate this. Pi is approximately 3.14. Sine of 2, well, if we think about the graph of sine, there's pi, 0, here's y equals sine x. Well, 2 would be somewhere around here, right? The key is you know for sure sine, the regular graph of sine goes between 0 and 1. And at 2, it's not exactly 0, it's not exactly 1, it's somewhere between 0 and 1. So maybe 0.8 or something. And you can see the key is, can you tell, is this in our interval or not? Is that between -1 and 1? Definitely not. Because the numerator is larger. So we can, based on that, we can say this the series diverges by the geometric series test. And your reason would be since r equals pi over sine 2 is not between -1 and 1. You also could have used the root test on this one. That would have worked as well, but I think in this case the geometric series might be a little easier. All right, let's take a look at the next one. So you've got e to the n over n. Well, it doesn't fit P series. This time you can see it's not geometric. It's not alternating. We don't have the negative one. So if you have something like that, and there's nothing we can just take off to simplify to compare it to with our comparison tests. There's not really a thing that we could take the root of easily that wouldn't simplify this. So in this case, probably the easiest way to handle this one is the ratio test. And there might be another test that works. You might be able to figure it out with another one, but the ratio test seems to fit the most, fit this one the best. So the ratio test, remember, you just find the limit as n approaches infinity of the absolute value, and you substitute an n plus 1 wherever there's an n, so e to the n plus 1 divided by n plus 1, and that's divided by the original formula, e to the n over n. Now let's simplify this. We have the limit as n approaches infinity, absolute value, and then we have e to the n plus 1 over n plus 1 dividing by that is the same as multiplying by the reciprocal n over e to the n. Then when you substitute in infinity, actually, let's simplify this first before we do that. Before we substitute infinity as much as we can. Well, n and n plus 1, that's like 6 and 7. We can't simplify those. But we have the same base here of e, and what we do is subtract the exponents. So e to the n plus 1 divided by e to the n, that'd be like subtracting the exponents, n plus 1 minus n. That cancels out the n's. You just get you just get 1. So it's just e to the 1. Well, that's already a constant. That's positive, so that doesn't get affected by the absolute value. And then remember the n's also don't, because those are going to be positive since we're starting at n equals 1. So those are not. So really, the absolute value doesn't affect anything here. So then we can just substitute in infinity. So e to infinity over infinity, which equals e, and that's greater than 1, so this diverges by the root test. Sorry, by the ratio test. So we could say the series diverges by the ratio test since our limit here as n approaches infinity, absolute value of e to the n plus 1 over n plus 1 divided by e to the n over n, because that limit was greater than 1. And I just realized as I was going through this that actually there was probably an easier test we could have used. So let's go ahead and see that on this problem there's more than one that you could have used here. I forgot that we could use the divergence test. Notice e to the n versus n. Let's find the limit as n approaches infinity. We've got e to the infinity over infinity. Well, which of those grows faster? The exponential one is much larger as we head off to infinity. So since that's the case, that's infinity, which is not equal to 0. So that would have actually probably been a little easier. So we could also have said the series diverges by the divergence test, or it's also called the Nth Term Test, since the limit as n approaches infinity excuse me, of e to the n over n does not equal 0. Oh, and my notation here, sorry, I was a little off here. I should have first written this as e to the n over n, and then that equals when we plug in infinity that. So either way is correct. Notice they give you the same result, that the series diverges. Here we use the ratio test, here we use the divergence or nth term test. Both are valid. All right, let's take a look at the next one. On this one, well, this doesn't seem to fit p-series, or it doesn't look geometric, multiplying by the same thing, not alternating. But if you take a close look at this one would be something we could integrate here. So let's try using the integral test. And remember the way we do that, we rewrite it 1 to infinity, and then 4n e to the negative n squared dn. And in order to integrate this, you can see this one, not in a form we can integrate right now. If you use u substitution, though, set u equal to negative n squared, and then convert our lower and upper limits to be in terms of u. So if you substitute infinity, you get negative infinity squared. Substitute in 1 squared is 1, but you have a negative there, so negative 1. And then we'll have 4n. Now we can write this as e to the u, but we need to replace the dn. So if we take the derivative, du dn equals negative 2n squared. So dn would end up equaling du over negative 2n. Replace that right here. And then you can see we can reduce that. The n's reduce out, which is what we want to get. We want to get all in terms of u. You can pull out a negative 2, but notice what happened. These are also now in the wrong order. So if you want, you can get rid of that negative by flipping this to be from negative infinity squared to negative 1. The 2 would now go on the outside. We got rid of the negative because we flipped it. And now we just have e to the u du. So then we have 2. When you integrate e to the u, that's the one that stays the same, just e to the u. From negative infinity squared to negative 1. So we have 2. Then substitute those in, e to the negative 1 minus e to the negative infinity squared. So we'll have 2, e to the negative 1 is the same as 1 over e, minus e to the negative infinity squared is the same as 1 over e to the infinity squared. Well, 1 over e to the infinity squared, e to the infinity squared is huge. 1 divided by some huge number, that's basically 0. So you have 2 times 1 over e. So the definite integral equals 2 over e. Since that's finite, that means the integral converges, which means our series will also converge. So we can say the series converges by the integral test since integral from 1 to infinity of 4n e to the negative n squared dn, you could say converges, you could say is finite, not infinite, either way. All right, let's take a look at the next one here. So on this one, notice we've got this whole thing is raised to the nth power. So when that's the case, that's your clue that probably the easiest test to use here would be the root test. Okay, so the root test says, well, let's find the limit as n approaches infinity of the nth root of our formula a sub n right here. So 5 plus 2n squared over 3n squared plus 1 to the nth power. And when you do that, notice those are going to cancel out there, and the nth root of the nth power. So we'll just have the limit as n approaches infinity. What's going to be left is just 5 plus 2n squared over 3n squared plus 1. And then if you substitute in infinity, we get 2 infinity squared over 3 infinity squared. Those are the terms that are going to matter. You can see the infinity squareds reduce out, giving us 2/3. And since that 2/3 is less than 1, that tells you by the root test, just like the ratio test, this series converges. If it was greater than 1, it would diverge. If it was equal to 1, it would be inconclusive, and we'd have to use a different test. So we can say the series converges by the root test since the limit as n approaches infinity of the nth root of 5 plus 2n squared divided by 3n squared plus 1 to the nth power is less than 1. All right, let's take a look at one more here. So you've got 3 to the n plus 1 to the n divided by n factorial. All right. So there's a lot going on this one here. So let's see if we can figure out what's happening with this. It doesn't fit, it's not altering, doesn't fit geometric. It's not one that you can easily take something out that doesn't matter to use a comparison test. It's not the p-series, so not specifically a root we could raise it to because of this here. So it's probably best to use the ratio test in this case. So let's use our ratio test. So this would be the limit as n approaches infinity, absolute value of 3 to the n plus 1. Notice we're plugging in n plus 1 where it's n. And then when you substitute n plus 1 for this n right here, plus 1, that makes it n plus 2 to the n plus 1, divided by, when you substitute n right there, the n plus 1 factorial. And then that's divided by the original one, right? But that's the same as multiplying by the reciprocal. So that'd be n factorial divided by 3 to the n plus 1 to the n. All right, let's see if there's anything we can reduce here. Well, first thing, so we'll find the limit as n approaches infinity. First thing we can do is look at the 3's. 3 to the n plus 1, 3 to the n. That's going to reduce out. I'll just leave you with 3 to the first, which is just 3. And that can go outside of the absolute value because it's not affected by that. Then we have n factorial, n plus 1 factorial. That's like 7 factorial and 8 factorial. You'd just be left with the 8. So those reduce out and leave you with just n plus 1. And since it's n, that's not going to get, and we're adding 1, that's not going to get affected by absolute value either. So that's going to be left on the denominator, n plus 1. And then right now, we can't reduce these right now. N plus 2 to the n plus 1, n plus 1 to the n, because they have different bases. So we'll just leave those, but they won't get affected by the absolute value because n here, our terms are always going to be positive since we're starting at n equals 0. So we'll have n plus 2 to the n plus 1 divided by n plus 1 to the n. Now, let's see, you could substitute infinity. Now, let's try to make this as simple as possible, though, before we do that. So the limit as n approaches infinity. Well, now notice we can combine those on the denominator. So we have 3, because they have the same base, n plus 2 to the n plus 1, over n plus 1 times n plus 1 to the n. This is like n plus 1 to the first. You would add the exponents. So that's n plus 1 to the nth power. Sorry, n plus 1 power. All right, now it's probably easier to go ahead and substitute in infinity. So we have 3. This plus 2 is negligible now, so it would be infinity to the infinity power over infinity to the infinity power. You can see those reduce out, leaving you with 3. And since that's greater than 1, by the ratio test, this diverges. So we could say the series diverges by the ratio test since our limit as n approaches infinity, absolute value of our 3 to the n plus 1, n plus 2 to the n plus 1, divided by n plus 1 factorial, and that's divided by, our original one was 3n, n plus 1 to the n, over n factorial, since we found that limit is greater than 1. And that concludes the notes for AP Calculus on the topic of the summary of the test to see if infinite series converge.